Hi, this example problem involves Newton's second law for rotational motion, and it actually includes a lot of different parts of rotational motion that we've studied so far in chapters 8 and 9. Pause for a moment so that you can read the problem. So you see that in this problem, part A deals with angular acceleration, B, moment of inertia, and C, the net torque. Newton's second law here for rotational motion, the angular acceleration is equal to the net torque divided by the moment of inertia. So this is related to this equation. In part A, we are asked to find the constant angular acceleration of the arm and the ball. So the arm and the ball are rotating here. Here's the axis of rotation, the elbow. And these guys can go ahead and rotate along here, right? And as they do, they're going to, go ahead and increase the angle. It's going to travel along, with some angular speed as that happens. And there's an angular acceleration as well that's causing the angular speed to increase as time goes up. We can find the constant angular acceleration here because the key word is constant angular acceleration. So we're going to use the method that we do use for constant angular acceleration. That means we're going to write down alpha, omega initial, omega final, the angular displacement, and the time interval. We're trying to figure out what the angular acceleration is. Let's see what else we know. Well, this is being thrown, and it starts from released, ball starts from rest, so that means that the initial rotation is 0. And it's released with a speed 30 meters per second. Are we going to put that right here? We can't put that there because that's a speed. What we know is that the final speed there, this is a tangential speed, is equal to 30 meters per second. We need to convert that to a angular speed. Well, the radius in this case is 0.35 meters. And remember, we can relate tangential quantities with angular quantities. All we need to do is to solve for the angular quantity, we take the tangential quantity and we divide by the radius. In this case, 30 meters per second divided by 0.35 meters. And this is going to give us our final angular velocity, which is 85.7. And now we know we cancel the meters out. We have 1 over seconds. We need to add back in radians, the dimensionless unit. So we've got 85.7 radians per second. We've got 2 things out of 5. We need to find a third one. Aha, here it is. The total time there, 0.3 seconds. Now we're going to need to find an equation that we can use to solve for alpha. We don't know delta theta and we're looking for alpha, so equation 1 is the choice that we're going to use here. Omega final equals omega initial plus alpha times delta t. And we know that the initial angular velocity is 0. And we can go ahead and solve this for alpha. When we do that, we end up with alpha is equal to omega final divided by delta t. And let's plug our numbers in here. 85.7 rads per second divided by 0.3 seconds gives us an angular acceleration of 285.7 radians per second squared. That's the answer to part A. Let's look at part B now. Calculate the moment of inertia of the system consisting of the forearm and ball. All right, so I've cleaned up the picture a little bit. We see the axis of rotation at the elbow, and it can rotate in this direction. And we've actually got 2 objects here. We've got the forearm and we've got the ball. And so to calculate the moment of inertia here, I, we're going to have to add together the contribution for the forearm and the contribution for the ball. Now for the forearm, we can treat this as a rod rotated about an axis. through the end. And you can see that would be the equation here, 1/3 ml squared. And for the ball, we can treat that as a point mass. And remember, the equation for moment of inertia point mass is simply m, the mass of the point mass, times the distance r from the axis of rotation, which is also L in this case. So let's plug in our values and see what we get. 1/3 times the mass of the forearm, which is equal to 1.5 kilograms, times the length of the forearm, 0.35 meters squared. And now for the baseball, it's going to be the mass of the baseball, 0.15 kilograms, multiplied by the distance from the axis of rotation, again, 0.35 meters squared. And when we put all those into the calculator, this is the answer we get for part B. We get 7.97 times 10 to the -2 kilograms meters squared. And there is our answer for part B. The moment of inertia of the forearm and ball system as it rotates. Finally, part C. Find the net torque, the magnitude exerted on the system that produces the angular acceleration in A. There, we're going to go ahead and use Newton's second law, and we want to deal with magnitude, so we'll go ahead and take the absolute value of the vectors there. And to calculate that net torque, we'll simply rearrange that equation. So sum of the net torque, I just need to multiply alpha by the moment of inertia. And that's the product of our answers for part A and part B. And calculating this gives us a value of about 22.8. And the units here are going to be Newton times meters for torque. And again, how does that come out? Well, we drop the rad because we're getting meters in there, and we end up with a kilogram meter squared divided by a second squared, and we just take out one of the meters, because in parentheses here, that's a Newton. And so there's our answer for part C.